Okay, so in this video lesson, what we're going to talk about a little bit more detail is these actual covalent bonds, or these molecular bonds that exist. Okay, so a couple of things to review. First of all, covalent bonding is that sharing of electrons, that we do so to obtain that noble gas configuration, or basically so each element can assume that they have 8 valence electrons in its outer energy level. So by sharing any electron that is shared, both atoms can then kind of count it as part of their 8. All right. Now, we also have this idea of how many can be shared. Okay, so there is kind of a limit to the amount of sharing that can happen. In a single covalent bond, or if you have one bond, that's a sharing of just 2 electrons. Okay, those 2 electrons could come from one each atom, or it's possible that one atom donates both electrons and the other atom doesn't donate any. So that's called a coordinate covalent bond, but it's still considered a covalent bond. Now, if you're sharing 4 electrons, we double that. We say it's called a double covalent bond, okay? And we symbolize that by a single bar or a double bar, okay? If you share 6 electrons, which is the maximum amount of electrons that can be shared, we call that a triple covalent bond. And again, we show that by 3 bonds in that. We distinguish this because the amount of sharing that is there actually has some repercussions on the energy and the stability of the actual molecule that's generated, okay? For us to talk about that, we need to talk about bond dissociation energy, okay? So in every bond, there's a balance between the nuclei repelling each other and the attraction of the electrons, all right? So if we take a look at this image here, if we have a simple, we'll call this a H2 molecule, hydrogen bonded to itself, 2 hydrogens, okay? In a typical hydrogen atom, you have 1 proton, 1 electron. So here's our proton, 1 electron. The other hydrogen has 1 proton, 1 electron in it, okay? Now, in this scenario, the 2 nuclei of our hydrogens would repel each other, repulsion. The 2 electrons would repel each other, repulsion. But there's also an attraction between this electron to both nuclei and this electron to both nuclei. So this attraction, in comparison to this repulsion, creates a certain length of a bond inside there. And it has to be kind of a perfect amount of length, okay? So if you imagine, my thumbs are hydrogen atoms, okay? And by themselves, they're all dancing all over the place. They all have all this energy with them, and they're really unstable, okay? So in this configuration, there's nothing controlling me. I'm all unstable. However, if a rubber band can represent that bond or that sharing of that one pair of electrons or 2 electrons, okay? So this is the 2 electrons being shared here. Each side represents an electron, okay? Now, my movement is stabilized, okay? So I still may want to stretch out or get tighter together, but I'm kind of stabilized inside of here by using this band, okay? So that bond creates stability. Now, by doing this, we actually lower my energy, all right, in terms of what kind of goes on there. If we take a look at what that means to us is, if we have over here, number 1, we got kind of read right to left is opposite of what we normally do in Western culture. We start off with the 2 hydrogen atoms, which are separate, and they have a certain amount of energy. We're going to call that energy point 0, okay? As they come together and get closer to each other, so we see them coming together, getting closer here, the actual potential energy that they contain starts to decrease. We see that graphically now it starts to decrease at point 2. Okay, now this energy becomes down to a minimum at point 3, which is the space between the 2 nuclei is 74 picometers, which is a tiny little measurement. Okay, that's considered the bond length. Okay, that's the length of the average bond in a hydrogen molecule, an H2 molecule. If we were to continue to push that length closer, so we pushed them closer, so the nuclei got closer and closer and closer, now that energy well that we created would dissipate, and we'd actually increase energy, and we'd actually get to an asymptote where it would exponentially increase, because they got closer and closer and closer. These positive nuclei would repel each other, and they would not want that to happen. So for every bond, there's a perfect length, okay? It's a reaction between the repelling of the nuclei and the attraction of the electrons to the nuclei, okay? So if we go back to this, it's kind of a balancing act between these 2 things, okay? So as atoms form covalent bonds, they release energy to become more stable. If we were going to go ahead and break that bond, then we would have to put that energy back in. So as the bond was forming, we lost energy and came down here to a lowest energy point, making it more stable. Less energy means more stable, by the way. If we were to break this, we had to input all this energy back in to get back to our 0 point. So taking energy in, okay, would be breaking a bond. As you form a bond, you release the energy, all right? Finding that perfect balance or that perfect distance between the two is called our bond length. Now, because of that, we have something called bond dissociation energy, or the energy required to break a covalent bond, okay? That is measured in kilojoules per mole, okay? The larger the bond dissociation energy, the more stable the molecule is, okay? It's also related back to the length of that, all right? So let me kind of go back to my rubber bands and my thumbs here again. If my thumbs are, again, 2 carbon atoms now, we'll call them carbon instead, and I have a single bond between that, okay? If I pull outwards, representing a certain amount of force pushing away from my 2 nuclei, I can stretch my rubber band a certain distance if I use a certain amount of strength, okay? However, if I were to add rubber bands, so I put a second rubber band in and I pull outwards with the same amount of strength, I can't get it to go out as far, okay? Originally, I had it way out here. It was this wide, pulling with a certain amount of strength. You have to trust I'm using the same strength. At the same strength, I only can get it to go this wide now. The reason being is that balance is now shorter, okay? Because sharing of more electrons creates a stronger bond dissociation energy. If we go even more, we go to 3, where I'm now sharing 6 electrons, or I have 3 bonds, it's even shorter for that same amount of strength. So each additional rubber band or each additional sharing of electron creates a bigger bond dissociation energy, okay? So if we take a look at this data down here, we see single bonds are going to be our longest ones. They're going to be the ones that are furthest apart. They're going to have the lowest dissociation energy, which means they're the easiest to break, okay? Double bonds are in the middle, so which means they're a little bit harder to break. A triple bond is going to be the shortest of all our bonds, which means it's going to have the highest dissociation energy, which means it's going to be the hardest to break, okay? Now, the take home from that is that the shorter your bonds, they're stronger, they're more stable, and it takes more energy to break them, okay? It also means that when you form them, it releases more energy, okay? So forming triple bonds tends to release the most amount of energy when we work with things, okay? These are some numerical data to kind of show their representation. So the carbon-to-carbon bond, a single is 154 picometers apart. The double bond is only this. The triple bond is this. And if you look at those different energies in that, right? So kind of the take-home here is that things that are triple bonded tend to be more stable than things that only have a single bond in them. Okay, so things that are triple bonded tend to be more stable than things that have a single bond or double bond in them, all right? That plays a role because stability is the ultimate goal for all of our elements. So they want to become as stable as possible or get to the lowest energy state possible. So to get to the lowest energy state, triple bonding is preferred to do that, all right? All right, guys, that is bond dissociation energy and kind of how that works.